What we're doing is we are recording force and distance. We're used to having force be the same as the distance stays the same. But what I've got set up here is a vernier motion or detector system with the motion plotter here, and then over on this side I have a force sensor hooked up to a spring. So what we're going to do is notice how the force changes on the spring as the distance increases. So we're going to be graphing two things, and then we're going to relate them in our experiment to each other. So here we go. So I'm going to have the spring stretch, and if you notice, the force on the spring is increasing as I go along here. Now I tried to make the position change the same, but as you can see, I was slowing down towards the end because it was getting harder to pull the string as tight as it was before. I'm going to save that run. And I'm going to try, let's see, file, save. I'm going to try it again. And let's see here, experiment, new run. So start collection. Here we go. This time I stretched it a little bit too soon. I'm not going to count that one, because that one, I'm going to have to go slower. That's the problem, because I pulled the string too tight too soon. So here, let's try this. That looked like a pretty good run, so I think I'm gonna keep that one, and then we'll go on and do the rest of the experimentation.
Alright, so we have here the experiment that we've done so far, and if you notice, we've got the position graph up here on the top. That was taken from the motion plotter, and then the force graph in red here down at the bottom, that was taken from the force meter. We get the linear fit for each of them, and one of the problems that we have with the position graph is that we were measuring as you were getting farther away from the spring, and really we should have had it graphed the other direction. So what I did is I made a distance graph that was corrected, and if you notice here, it is just like the distance graph that we had before, but there's two differences. One of them is it's got the reciprocal slope. Actually, it's a little bit different in the reciprocal slope, but it's got the intercept is also corrected, because what I did is I took the differences or the distances that they had, took the product of -1 in that distance, and then made sure that it went through 0, 0. Actually, it goes through, if you notice, 0.0065 here. So it's a little bit below 0, but not, that's 6, what is that, 6 millimeters? So it's not very far off. Okay, so what I did then is in order to calculate the work that we are working on, the work equation, we're going to need to compare the distance on the horizontal axis versus the force in the vertical axis. And if you notice, the distance goes from 0 to 4 and the force goes from 0 to 10. So I've got the intercept and the slope here, 26.45. In other words, the spring constant is 26.45 newtons per meter. So let's go back to Desmos and let's see our different graphs. So first of all, the easy one is the force graph, and all I did is I wrote it as a piecewise function because I didn't really start pulling until 2 seconds into the experiment, and I pulled till 10 seconds, and as you can see, the graph came out to be pretty much linear after that point. The other graph that I did is here's the distance as the force detector gets closer to the motion detector, and then instead of that though, I plotted it going away. So it starts out at 0 and then it goes away. So the distance formula that I'm going to use is the second one, negative or positive 0.4982. So now I'm going to show you the graphs of those two things. So I graphed the force as the horizontal axis and the distance as the horizontal axis and the force as the vertical axis. So I have force as a function of distance, and then it's 26.45, that's the slope of this line, and then its intercept is negative 0.954, and that's mostly related to the fact that the spring didn't start stretching until I had started pulling a little bit. All right. So once you get that, then you can get the integral, that is the area under that curve. And the integral of that, as you can see, is a quadratic. I just integrated 26.45s minus 0.954s. And actually, I can... Ooh. What did I do wrong? Equals. I thought I could just do less than. Let's try it this way. Y is less than 26.45 S minus 0.954. Oh, X. And as you can see, I should change the color of my sliding. There we go. That'll be better. So, oops. So you can see the area under the curve is shaded there in blue, and that is the area of our triangle. And if you notice, it doesn't make sense before you've got a distance of 0.0361 about before it starts making sense. Okay, so I'm going to turn off that function, and as you can see, we've got, and I'm going to turn off the shaded function too. So we've got this curve right here, g of s. So if I find g of 0.2 and g of 0.4, you notice my value at 0.2 here is about 0.33 newtons, and my value at 0.4 is much greater than twice that much. It's actually 1.729 newtons. So the work gets harder to do the farther you've pulled the spring.